So I think I can start already. Hello, everybody. Thank you for being here, both physically and virtually. So my name is Leonardo Linguaglossa. Some of you may know me have known me for a long time. I am currently associate professor or maître de conférence at Télécom Paris. But ever since I finished my studies in 2012, I joined Links first as an intern student, then as a PhD student, finally as a postdoc. I have changed 3 affiliations, at first with Nokia, then with INRIA, and finally with Télécom Paris. And in these 8 years, I never changed my office, which is basically the same ever since. So today I am going to present my ongoing work on the inference of high-speed networks, of which I am an expert, via machine learning, of which I am not an expert. It's a new...
Sorry, I was disconnected on my PC, so now it's okay.
Okay.
So I will...
Yeah, so I was finishing the presentation of my ongoing work.
Okay.
Then I would like to give credits for this work to my collaborators. I have hired 2 intern students during 2018-2019 from UCL and from University of Tehran. I have collaborated also with people from NTNU, University of Würzburg, as well as Nokia, Airbus, and Technical University Munich. And my results have been published at many conferences, such as Infocom and other journals, such as Comnet and Transactions on Networking. Now, let's start with the topic of today's presentation, which is the evolving domain of machine learning. We have experienced impressive improvements in the last decades about the evolution of machine learning algorithms. We have been going from simple pattern recognition to advanced generative adversarial networks, which are able to create new items that were not visible from the original dataset. And in fact, I was curious about this. I have had a look at the system developed by NVIDIA, which is supposed to create images of cats from after a training with thousands and thousands of images from the internet. And I have understood there's still much to do, because when you ask these algorithms to create the image of a cat, this is what you obtain. So basically, the algorithms have understood that a cat is basically a piece of components with a top stripe and a bottom stripe with some text in the middle. And this is because it has been trained with the images gathered from the internet, where the majority of the topic is basically memes and jokes about cats. So there is a problem with current algorithms that I summarize here. First of all, about the data quality, because not everything that you find on the internet is gold. About the labeling, because so far, the majority of it is still manually done. So there is still a human who is responsible for classifying and put a label on images, which is a very error-prone procedure. Then currently, most of machine learning techniques target very human-centric objectives, such as recognize the picture, recognize the song, and this kind of problems that involve humans in the loop. And we will see what that means in the rest of my presentation. Now, I am a network guy, and as a network engineer, I quickly understood that machine learning for networks can really become a new field of studies. There are many differences between pure machine learning, if you want to call it like this, and what you apply in network systems. First of all, there is a huge difference in the time scale. It is much smaller for networks and especially high-speed networks. And in fact, since classical machine learning has a strong component linked with human beings and human behavior, you do not have this kind of thing with machine learning for networks. And the time scale of 300 milliseconds, which can be a blink of an eye for a human being, is in fact many ages for computer networks. Then a second aspect is linked to the data collection capabilities. We are used to think about data collection as a simple but very long task. In fact, it is not that simple, because in networks, even the data collection can significantly alter the state of the system. Think about regular application with a relatively normal speed of 14.88 millions of packets per second, which is a typical rate of 10 gigabit per second line cards, not the fastest line cards that you have in the markets right now. And within these characteristics, you can immediately observe that the processing time for each packet is of few nanoseconds. And if you consider that CPUs are not so different than 20 years ago, even a single clock cycle of alteration can significantly change the state of your system. Finally, computational power is a scarce resource. We are used to think about unlimited capabilities of our machines, but in networks this is not the case, and often you may not have the option to offload some computation to external CPU, because it will introduce latency. And in general, machine learning for networks should favor more parsimonious usage of resources. We will observe this trade-off in the later part of my talk. So I hope that I convinced you that this is a relatively new problem, and I am actually continuing my research in this domain. I started with a small grant that I received last year from the German-French Academy. It's a collaboration between France and Germany. And and afterwards, I've been hired as a maître de conférence, as an associate professor with to work on problems linked to machine learning for networks. And basically, this is the outline of my talk. I will first introduce you the problem of high-speed software networks and machine learning. I will talk about the so-called data uncertainty principle, that paraphrased the more famous Heisenberg uncertainty principles. And finally, I will show you the application that I found, that is inferring networks behavior from indirect measurements. And I will finalize the talk with the ongoing work and some of the use cases. Now, let's start about high-speed networks. We are currently observing a process of ongoing softwarization, which advocates the replacement for hardware middle boxes towards more flexible components based on pure software. So everything that you know belonging to networks, such as switches, routers, and firewall, are slightly becoming pieces of software executed on top of commodity servers, so with a regular operating system on top of which several applications can coexist one with each other. Now, there is a clear trade-off between the performance provided by hardware solutions and the flexibility provided by software. This gap has been filled in the last decades, and it has fueled the growing popularity of items called software routers, which are basically pieces of software that executes network functions, from the forwarding to the routing to the firewalling, and every kind of application that you can think about in networks. So you basically replace all of your middle boxes with a simple commodity server equipped with one or more network interface cards, so that with equipped with wires and transceiver. And from the logical components, you have the user space application, that is exactly what you want to deploy on your server, which abstract some of the functionalities provided by the low-level components, such as the network interface card, the hardware queues, and it provides also the mechanism to route and steer traffic from and within and towards the network interface cards. Now, software routers were born as a way to prove the flexibility of software with respect to hardware solutions. But we are now seeing that they are steadily being implemented on different domains, ranging from the access networks to the cloud to CDNs to even relatively different telecommunication networks such as 5G or wireless. Now, imagine to have these huge capabilities of data, collecting data and quickly modify the behavior of your system thanks to the software nature of these components. The first thing that you can think is that once you have high-speed software networks, you can try to put some more intelligence in it. And now, what that means? It means that if you have, you can adopt a typical machine learning approach for solving some problem. You have a problem, then you start collecting some data and you iterate on this part. You can decide to introduce labeling if you want to adopt a supervised learning approach or not. Then you choose a model to solve your problem. It could be an optimization problem, it could be a resource allocation problem. You can decide even to have more reinforcement approaches. You validate your model, and finally you end up with a tuned model that can be used to make predictions for a certain application. Now let's focus on the theoretical part of this approach. We have several humans in the loop because, as I said before, most of the data collection is still manually done. Most of the modeling part is there's still a human in the loop. In fact, for the data collection and labeling part, the manual procedures are a source of errors. They are difficult to automate, and especially for networks, they involve a large scale that a human cannot possibly fill in. As for the training and validation part, we still have humans in the loop. The model selection can be difficult, but the training can be automated if you want. And finally, once you deploy your machine learning application, you have a tuned model. So all the heavyweight part has been done before. Humans can be removed from the loop. You can just leave your model alone. And the execution time is supposed to be much less than the previous parts. But is it really like this? Let's make an example. So imagine that you have a situation like this with an automated elevator equipped with a regular CPU, and the objective of your machine learning is to open or close the door if it recognizes or not a face. So you have a corridor, a 10-meter corridor. You walk at 3 meters per second, and so as soon as you start walking towards the elevator, your model must run the previously trained pattern recognition algorithm, and it can decide to open or not the door. Now, the time scale involved are of seconds, and the execution time may be sub-seconds. But now, let's make an example with network. You basically replace the corridor with a network cable, a 10 gigabit per second link. Your face is not a face to be recognized, but is a traffic pattern with packets to be recognized. A relatively low speed is 10 millions of packets per second. And now you need to do exactly the same thing. Send a signal if it recognizes pattern or not. Now, if you use exactly the same algorithm with offline training on traffic recognition instead of face recognition, we observe immediately that the time scale is already of sub-microseconds and the execution time is of nanoseconds. And if you consider that a single packet may take 200 clock cycles to be processed, you can understand that a full pattern, in order to be recognized, it can take several ages with respect to this time scale. And if your application is not to close or open a door, but it is to detect an attack, an ongoing attack, you understand that this can be quite complicated. So basically, in order to bring machine learning to software networks, we need a fast collection of high quality data, but not only. We need also to automate the labeling as much as we can to avoid misclassification and miserrors. We need to remove humans from the loop. And as a final point, the execution time itself is challenging with respect to regular applications. And so this can allow me to ask, to question, is there a limit for the machine learning processing and the software nature of network functions? And I ended up with this idea of the data uncertainty principle. It is not a technological limit. I will show you what it is about. And it significantly affects the feasibility of machine learning solutions for softwarized networks. Now, I have talked about software routers. They are pieces of software that can, in the end, receive and send packets. And this is what happens regularly. You have a network interface card. You receive packets from the network interface card, then the software router pulls the packets from the hardware. This is usually done in batches to speed up the overall processing. You get one full batch of packets, and then you either forward the packets to the next hop, or you start doing some processing. But everything that is happening here is software. And so the software has basically two states. One state that is the polling part, the polling phase where you periodically check for packets to the network interface card, and then a processing phase where you decide to process the packets or to forward to the next hop. And you iterate this loop over and over again. The code is written in some language such as C or Lua or Python. The code is either interpreted or compiled into a CPU, and this compilation and interpretation process means translation from a high-level language to a machine language. So in the end, your code is transformed into a set of assembly instructions that are executed on top of CPUs. All right, so where I am going, I think you can already imagine, because those instructions are executed within the CPU. It is indeed a very complex systems with several pipelines of different stages. You can maybe recall the stage of the instruction fetch, the decode, the write back stage of classical CPUs, the arithmetical logical unit, that is the unit devoted to the actual computation of the low-level instructions. And so your code is transformed into this series of instructions that are executed with respect to the clock cycle, the clock signal of your CPU. I was talking about a CPU of 2 gigahertz. This basically means that it can issue 2 billions of clock cycles per second. On correspondence to each clock cycle, your pipeline stage can progress until the final instruction and the write back of the operation. Now, this is what happens with your code that is only doing the packet processing. Now, let's start thinking about making some measurements, no matter which kind of measurements, even from counting packets or from just detecting a single flow in a series in a traffic pattern. Now, I will identify with red color all the clock cycles that are used for measurements. When you start making measurements, some of the clock cycles that were previously utilized for the processing are now utilized for doing the measurement. And therefore, your whole pipeline is going to be shifted. This means that you are altering the system. And the more data that you want to collect, the more altering you may perform. And if you think that complex analysis require a lot of data, complex analysis means more altering. And this is something that is not a technological limit, because if you had many more clock cycles, you will still need to allocate some of the clock cycles to do your measurements. And as there is no free lunch in this world, you can of course use a different CPU for doing the measurements, but you're not. You are basically doubling the resources for doing something that would need just a single CPU to be executed. So measurements operations will inevitably alter the state of the system, and the cost of measurements depends on which kind of measurements you are performing. In this slide, I show you the cost of measurements of a single virtual network function, abbreviated in VNF, executing simple cross-connect. That means send all packets received from one input interface towards an output interface. And I show you what is the evolution of the cost of this function, starting from the simple baseline. So all packets are sent towards the interface, and that's it, to a more complex scenarios. Here you can see the number of clock cycles per packet on the x-axis, and you can see that when you start counting all packets, you introduce a little bit of overhead, and this overhead becomes more and more heavyweight as soon as you start hitting different components of your underlying server architecture. So as long as you use simple counters, your impact is low. When you start accessing the RAM, such as what happens when you consider hash function and the flow hashes, then your overhead becomes greater. Finally, if you access the storage, that's the worst case scenario. I am showing what is the impact of exporting the data every 5 seconds, and the cost of your network function is already 3 times as much as it was on the baseline. Think about that. If you want data, you need to export this data eventually, because otherwise you cannot operate on with any kind of offline mechanisms. So the so-called data uncertainty principle means that not everything can be monitored in software without inevitably altering the state of your system. And the higher is the rate of your high-speed application, the higher is the effect on the uncertainty. It is essential for this to build monitoring tools that cleverly use the resources in order to minimize the impact on the measured states. And on the other hand, it is also necessary to find other ways of measuring of the measurement process in general for high-speed networks. And that is what we try to achieve with this project. So we understood that collecting data at very low level is complicated in networks. What if we could get some data via indirect measurements? So what I mean by indirect measurements, I mean that your server is also performing a lot of measurements on its own without dedicating, without especially utilizing clock cycles to make those measurements. What if we can interpret this data in order to infer the network state of the function that we are deploying? In order to understand this concept, think about the expressive power of languages. Now, in natural language, it's clear what you want to achieve, but not how to achieve it. Because you just say, go get that item from the registry, You understand what are the verbs, you understand what are the subject, what is the object of your sentence. Then, on the contrary, in machine language, in assembly, you do not have this expressiveness. You need to explicitly write a sequence of CPU instructions to be executed. Thankfully, there are some intermediate steps like formal languages or programming languages such as C, which provide you the good abstractions to write algorithms, which are somehow midway between the natural language and the machine language. What I want to show here is that there is a trade-off between the expressiveness of the language and the efficiency, if you want, of this language. Or in other words, the easier it is to describe, the harder it is to do it fast. And thanks to this observation, we can understand that in modern systems of software network applications executed on commercial off-the-shelf servers, you have low-level entities like NICs, CPUs, that are performing very simple data that are difficult to interpret, like single pixel of an image. If you isolate that pixel on its own, it's very difficult to understand what was the global picture. And at the same time, you have high-level entities that are represented by the software network functions or the applications, which, on the contrary, operate on complex data with an easier interpretability, because they have a higher expressiveness. And so what we can try to do is to link those two elements in order to get an inference of what is the state, the global state of the system, just by adopting only low-level entities. And in order to get to this point, we can collect data from the bottom, analyze from the top, and utilize machine learning techniques to connect these two worlds. So on the one hand, we have low-level entities that are easy to monitor but hard to interpret. And on the other hand, we have high-level entities that are hard to monitor, but they can be easily interpreted. And with medium, let's say, data availability. So what we end up with is network data fingerprint. So imagine to collect a lot of low-level features from your CPU. I will show examples. For instance, your CPU is already automatically counting how many instructions per second it is executing, how many branches the code is traversing, how many cache hits, miss it is performing. And all of these low-level features, they are easy to monitor because your operating system is already doing that for you. You do not need to write explicit code for doing that calculation. It is done without interfering with the regular processing of network applications, because you do not need to write code to do that. It is already performed at hardware level by your CPU. And imagine to get all these low-level features one by one and organized in an array. And this array will change as a function of time. We can try to get a correlation between the low-level features, so how many instructions per second, how many branches, how many cache hits you had, and the high-level state of your network function. For instance, the network function of forwarding is behaving at a very high load with a 20% loss rate. So you can collect all these features. You can use machine learning techniques to infer, to detect what is the correlation between the low-level features and the high-level state of the network function. And in the end, you can use your trained model to make predictions or, for instance, to allocate the correct number of CPUs in your system, to adapt the bandwidth with respect to some limitations or some fluctuations of your rates. So I proposed this AI-assisted optimization in software networks. I will show you a use case and a preliminary result. So first of all, let me start with the system abstraction. Now we have on the top different applications. As I said, an application may be simple forwarding, it can be an IPv4 routing, it can be a firewall. In current softwarized networks, all those applications can be deployed by means of a series of virtual network functions. And in the end, virtual network functions are executed on top of a CPU, which accesses an incoming, an input network interface card and an output interface card where packets can flow. We actually deployed these on a real hardware, on a real commodity server equipped with 2 line cards, one from input and one from for the output. Our line cards are 10 gigabit per second line cards, corresponding to about 15 millions of packets per second. We implemented different virtual network functions, so Ethernet, IPv4, and IPv6 in this case. And we wanted to, in this particular case, we wanted to match the particular input rate to a different scenario in order to speed up the processing rate or to slow down the processing rate to phase to some oscillations in the system. First of all, one simple observation is that in this kind of batched system, when you have a low rate at input, your batches will be small because the polling system will be faster and faster, and in the end, it will generate smaller batches. On the other hand, when the input rate is very high, your batches will be bigger because in the end, when the system is on saturation, it can start dropping packets, and this means that there are always packets waiting in the queue of the network interface cards. So now our objective is to detect the traffic conditions by only understanding how well the CPU is processing those batches. So the processing behavior of the overall network function reflects to the CPU. We can measure the state of the CPU, and in the future we could use this knowledge to adapt our rate without doing any material measurements on the input rate, because we only observe what is hardware calculated directly at low level on the CPU. Now, a simple scenario is the one that I'm showing you here in this slide. We have the experiments take 2 parts. A first part where there is a very low rate scenario, a very low rate on our input. And the second part, we inject a very high rate on our input line cards. And I am showing you the evolution of 3 of the possible features of our CPU. The number of instructions per second, the number of branches per second, and the number of branch misses per second. We can show that different features can be associated with different behavior. For instance, we observe that the number of instructions, they decrease a lot when the processing starts to become heavyweight. Some other features may be linked to the change in the steady state conditions, like the spike here on the number of branch misses to then become steadily stabilized at a certain level. Some other features are only slightly linked to any change at all of the system. So from this starting point, we started a behavioral study of many different conditions of our system. So we analyzed a lot of CPU data, from number of instructions, number of branches, to the CPU caches, to the number of misses, the number of exchange within the local buses of the CPU. And we started understanding how this feature change with respect to many different independent variables. For instance, in this case, in the previous case, I've showed you how they evolve as a function of time. Here, I am showing you how the feature per second evolves as a function of the input load rate. We can see that there are, of course, several non-linearities, which makes it very difficult to adopt standard models to analyze this behavior. But the good point is that all the features that we took into account, they can somehow be linked to a steady state condition of our system. And so they can become discriminant, they can become the sole predictors of the CPU, of the state of our network function. So in the end, our workflow is as follows. Our problem is that we want to infer the input rate of our system for making some resource optimization. We do the data collection by means of CPU fingerprint, which does not involve any actual measurement on the input rate. Our labeling is automated because everything is written in software that is less error prone. We choose as a model several neural networks, from simple multi-layer perceptrons to convolutional neural networks to long short-term memories. And in the end, we have a tuned model, and we can automate our runtime for the resource allocation in order to predict what is the optimal state of our system. So our experimental methodology is as follows. For the trained and validation, we use the pre-label data set, thanks to the capabilities of our CPU. The model is trained to predict which traffic class can match to the different CPU fingerprint data. We validated the model and we kept track of the accuracy. The model is saved. And after that, we wanted to run this model on our regular testbed. So we load the model, we perform predictions at very high speed, and we wanted to keep track of the processing rate and observe what is the trade-off between the accuracy and the processing rate. So the problem here is twofold. First, on the first part, we wanted to show the feasibility of this approach. So it is possible to learn what is the high-level network state by solely using CPU features. And on the second part, we want to show how this impacts the system at production level. So for the first part, our preliminary results are encouraging. Here I showed you the ROC score. Actually, this is the accuracy of our long short-term memory in different scenarios. Here on the left column, you have a training traffic, and on the right column, you have on the rows, you have the training patterns, and on the columns, you have the predictions. So FX means a fixed rate traffic. FXL means fixed rate traffic with long packets. We selected several kind of patterns like Poisson traffic. We got traffic data sets from packet injection attack, from data center communication, and in the end, we have trained our model with all these traffics, and we wanted to make prediction on the other classes of traffic. We first observe that not all traffic classes can be used as a training input, because the results cannot be satisfying. Here we had 40% of accuracy, which is not very high. We had only 3 classes, so it's only slightly better than a random guess. But on the other hand, some other traffic patterns can be easily detected by, for instance, training only on Poisson-like traffic. So in the end, we observed that it is possible to learn this, but to learn how the traffic behaves by using only CPU fingerprints, but it is very hard to detect what is the correct training that you can do in order to make exact predictions. As a second point, assuming a neural network model with n network layers, we wanted to show how the accuracy performance trade-off occurs. So now, offline, we have our model. We are able to detect our traffic classes, how this behaves in regular systems. So here you can, on the left plot, I am showing the accuracy performance trade-off in terms of classifications per second as a function of the number of hidden layers. You can see that when you start to augment or to increase the number of hidden layers, of course, your number of classifications per second is decreasing. You usually increase the number of hidden layers to increase the accuracy of your model. But this means that when you start to deploy your model on top of regular hardware, you can go from almost 70,000 classifications per second to only 30,000 classifications per second. So more than a half of a drop. At the same time, here on the right plot, I am showing the accuracy as a function of the operations per second. So basically, it means that if you want to achieve high accuracy, you need to reduce your number of operations per second. And if you want to increase the speed of your system, you inevitably end up by reducing the accuracy of your system. There is, of course, something that is involving also the processing limit of your hardware, but this is out of the scope of this presentation. So in the end, what we end up is with something like this. Suppose that you have analyzed the CPU fingerprint of three kinds of traffic. A is Poisson traffic at 3.5 gigabit per second with 256 byte packets. The B is Poisson traffic at 7.5 gigabit per second with 64 byte packets. And the C is constant bit rate traffic at 5 gigabit per second with IMX packets. So those are three scenarios that you can have on high-speed network applications. And here I am showing you all the features at steady state, so after the transient period is already passed, of which I am showing you the deviation with respect to the average measured in a number of standard deviations. So this means that a gray value is basically not very different from the global average of that features for all of the experiments. Yellow green standard deviation means that we have a huge deviation, and on the contrary, the blue violet is a negative deviation with respect to the average. And we can see already that those, if we arrange all the features one by one, side to side, with this kind of coloring, we can immediately see that there are some features that do not change a lot, with respect to different scenarios. There are some other features that are completely different at each of the scenarios. So the good point is that this can be a discriminative point for doing the predictions. The hard work is to make this happen at very high speed and without altering the state of our system. So this concludes my talk. In the end, machine learning for networks presents different challenges than regular classical machine learning approaches. In this particular case, I've showed you that it merges different know-hows for different communities, going from data science to the hardware-software systems. Machine learning in networks can be used for a plethora of purposes, some of which involve removing humans from the loop, and in order to reduce the error-prone, the number of errors in all the process for the machine learning workflow. It can be used to extrapolate unusual patterns from low-level data without involving any kind of hard-coded measurements. It is a hot topic in both academic and industrial communities, and I want to particularly focus on the challenges that interest me a lot. So first of all, the high-speed data collection and labeling, because while for the moment we only did this step offline, it could be possible to continuously monitor and collecting data at runtime. How to increase the data quality by removing humans from the loop. We have seen that so far humans are still involved, at least in the choice of the model. How can we get rid of humans somehow? Low impact measurements are also of greatest importance in this part. And I talked at the beginning about human-centric objectives, like recognizes faces. I think that we need a new perspective of network-focused machine learning, so some problems that are not human-centric. As for the opportunities, we can see that this can generate new business models for companies and network operators, especially on the planning part, on the multi-tenancy part of softwarized networks, on the resource allocation part, and how the monetary exchanges are involved with this kind of operations. Another opportunity is that it can boost innovation in some pretty static field like data collection, management, and usage, which are still involving a lot of manual procedures. It is, of course, a joint industrial and academic interest, and as a new member of Links, I am open to collaboration. So if you think that this can be interesting also for you, feel free to contact me and check my website. Now, if you have any questions, I am happy to answer.
So, any question in the room?
Any question in the room?
So you make this parallel between like the world of concepts where you have faces, you have cats, you have dogs. The question I have is, what are your traffic classes? How do you train something which may have, let's say, a multitude of definitions which are not really clear because you used yourself for like Poisson traffic at a certain rate, which was different from Poisson traffic at a different rate. So how many, let's say, combinatorial exploded classes could you have to train for, and which ones do actually matter?
So I repeat the question for the people in the on Teams. So Fabio is asking that the definition of traffic classes in my case was Poisson traffic, etc., but it can lead to an explosion of traffic classes. So somehow it's an arbitrary choice. Now, what are the classic traffic classes that matter? So this is a very good question, in fact, and so far we only focused on the general characteristic of traffics, so the ones that can be easily implemented with open source traffic generators. So you have traffic generator, and you can decide that you want Poisson traffic, IMX traffic, or constant bitrate traffic. This is, of course, a choice that is only linked to our testbed. But in the end, what I think is that the number of traffic classes that you may want to treat depends on your applications. So if you are a network operator that is mostly doing IPv4 forwarding, then you should use a dataset where your traffic classes can be found within the IPv4 domain. So you do not need maybe to use IPv6 packets or Ethernet packets or any or other kind of classes. You can just train your model with the data that your system is generating. So in the end, you just receive you do not receive all the Cartesian product of protocols and packet size. You only receive a partition of it. And so on that partition, you can decide to do some pre-analysis. So you can verify what are the traffic classes that are currently on your system, and then you can use that as a training for the system. But of course, yeah, you're right. It's a complex question, and this is just one idea that comes into my mind. Then the definition of traffic class is an important part, and this should be explored.
I have a question for you, Leonardo.
Yes.
It's Marco. Hi, everyone.
Hi.
So my question is, in your slide, if I remember well, 18, you basically says that you want to fetch a subset of packets to build your collection according to an a priori criterion in order to add to in the end to do some classification.
Mm-hmm.
So if you are able at this point to already extract relevant packets,
mm-hmm.
Does it mean that the classification that you are doing is not related to what are the interesting packets and what are the other one, or do you try to bring added value? So for example, does it mean that here you are basically, for example, extracting IPv4 packets, as you said, and later you are trying to find classes of traffic inside the IPv4 domain?
Yeah, so thanks for the question. In fact, in this particular case, yes, I was only doing the classification for the IPv4 packets, but of course the idea is that once there are two answers to the question. The first one is that first of all, I wanted to prove the feasibility of the approach and measuring how heavyweight this is in real scenarios. So independently for what the objective is. So this was the main one of the main objectives. The second answer to your question is that, of course, after you start collecting data without interfering with the system, you have potentially no bounds, no limits for what you can do. So at this point, I was doing the classification to detect those kind of traffic, but as the data is always the same, I can always decide at some point to detect other interesting metrics or combination of metrics. So I'm always analyzing low-level data, and low-level data, they have no idea of what a packet is. So then at high level, I, of course, project my problem. In this case, the problem was IPv4, but I can get exactly the same data as I was doing before, and then formulate another problem and use another model and train on another model and detect another model. So the data collection part does not change. It changes only the model and the validation.
But I guess that your filters must be very efficient if you don't want to make them become a bottleneck. So for example, if this is only extracting IPv4 packets, it's quite easy. But according to your curves in the last slides, if you use classification based, for example, on a neural network or based on a complex assembly program, as you shown at the beginning of the presentation, it might be very expensive to build your collections, and so the hardware might not follow if you have a high load of traffic.
So this is okay. It's a good point, and I want to highlight this because I wasn't clear maybe. And what you say is really true, because here, if you need to filter packets, yeah, you're basically screwed, because your filters must be very powerful. But what I am saying is that the notion of packets is only at the bottom of this abstraction. On the low level, I do not extract packets. I only extract information from the CPU that is already computed at hardware level. This means that if on a controlled scenario where I know exactly what packets I am injecting, I do not need to extract. I only need to measure what is happening on my CPU. And then, so this is useful because on your small test bed, you can calculate how the CPU reacts with respect to packets, such that on a real scenario, you can make the prediction without ever filtering packets.
But still, you have when you build your collection, you have to be quick, and those filters has to be simple, as you say, because otherwise it won't work, and your data collection will probably miss some packets because it's too slow. And yeah, and so my other question is, do you plan to do streams for your data collection, and so you try to train streaming algorithm to improve their quality, or do you rather plan to build batches of data collection? You train your models with those batches, and so what is the idea? Maybe the both?
So I think that batches are easier because it's more similar to what is the regular workflow of this kind of applications. So of course, when you use batches, then another question is how big is the batch that you use, etc. So I didn't exactly look into streaming algorithms, but I'm interested in exploring that part as well. But for the moment, I was only planning to do the data collection with batches.
Okay. Okay, thank you.
Thank you.
Other questions?